As we have learnt earlier, a constant current carrying conductor produces a magnetic field around it, and a change in the magnetic field with time induces an electric current in a closed conducting loop. Maxwell showed that a change in the electric current or the electric field with respect to time produces a magnetic field. To calculate the magnetic field produced by the change in the electric current with respect to time using Ampere's law, consider the process of charging a capacitor C by connecting it to a time-dependent current IT. As a first case, consider an imaginary circular loop S1 of radius r, which is outside the capacitor. The plane of the circular loop is perpendicular to the direction of the current in the conductor, and the center of the circular loop coincides with the conductor. The magnetic field due to the current in the conductor at any point on the circular loop is along the circumference of the circular loop. The magnitude of the magnetic field at any point on the circular loop can be calculated by using Ampere's circuital law. Consider a small element dl at a point P on the circumference of the circle. Let B be the magnetic induction at the point P. From Ampere's circuital law, integral over the closed loop B dot dl is equal to mu naught IT. Since B dot dl is equal to B dl cos theta, Ampere's law can be written as integral over the closed loop B dl cos theta is equal to mu naught IT, where theta is the angle between the directions of the magnetic field B and the small element dl along the circumference. Since the direction of magnetic field is along the circumference of the circular loop, angle between the magnetic field and the length of the element dl on the circular loop at that point is 0 degrees. Cos 0 is equal to 1. Then, integral over the closed loop B dl is equal to mu naught IT. Let this be equation 1. The circular loop is symmetric with respect to the conducting wire. Hence, the magnitude of the magnetic field is constant at any point on the circumference of the circular loop. That is, B into integral over the closed loop dl is equal to mu naught IT. Here, integral over the closed loop dl is the total length of the circular loop. That is, the circumference of the circular loop. Thus, integral over the closed loop dl is equal to 2 pi r. Let this be equation 2. Substituting the equation 2 in the above expression, we get B into 2 pi r is equal to mu naught IT. Hence, the magnetic induction B is equal to mu naught IT by 2 pi r. Let this be equation 3. Using the equation 3, we can calculate the magnitude of the magnetic induction at any point on the circumference of the circular loop S1. Now, as a second case, consider another surface to calculate the magnitude of the magnetic field at the same point P using Ampere's law. Consider a surface S2 in the shape of a cup such that the bottom surface of the cup lies between the plates of the capacitor and the open surface of the cup coincides with the circular loop taken in the first case. Let the point P be on the open surface of the cup. The surface S2 which is in the shape of cup, does not touch the conducting wire and the plates of the capacitor. Thus, the current passing through the surface S2 is equal to 0. From Ampere's circuital law, integral over the closed loop B dot dl is equal to mu naught It. Since the current enclosed by the surface S2 is 0, integral over the closed loop B dot dl is equal to 0. Hence, the magnitude of the magnetic field at point P on the surface S2 is equal to 0. Thus, Ampere's circuital law gives two different results at the same point P. In the first case, the magnetic induction at point P, B is equal to mu naught into It by 2 pi r. In the second case, the magnetic induction is 0 at the same point, which is a contradiction. This contradiction arises with the use of Ampere's law, which must be missing some term. Then Maxwell suggested that on close observation of the surface S2 between the plates of the capacitor, we can write the missing term in terms of the electric field that passes through the surface S2. This electric field produces some current between the plates of the capacitor. Now, let us calculate the current due to the electric field between the plates of the capacitor. Let A be the area of cross-section of the plates in the parallel plate capacitor. Q be the charge on the plates of the capacitor, and sigma be the surface charge density. Then, sigma is equal to Q by A. Let this be equation 4. We know that the electric field between the plates of the capacitor E is equal to sigma by epsilon naught, where epsilon naught is the permittivity of free space. On substituting the equation 4, we get E is equal to Q by A by epsilon naught, which is equal to Q by A epsilon naught. Let this be equation 5. Here, the electric field is perpendicular to the plane of the bottom surface of S2. Hence, the area vector of the bottom surface of S2 and the electric field are in the same direction and maximum electric flux passes through the surface. We know that from Gauss's law, the electric flux through the surface phi E is equal to EA. Here, A is the area of the surface through which the electric field passes, that is, equal to the area of the plates of the capacitor. On substituting the equation 5 in Gauss's law, we get the electric flux phi E is equal to Q by A epsilon naught into A. That is, the electric flux through the surface S2 is equal to Q by epsilon naught. Let this be equation 6. Equation 6 can be rewritten to get the charge on the plates of the capacitor, that is, Q is equal to phi E into epsilon naught. Due to the time-dependent current source, the charge on the plates of the capacitor changes with time. Thus, the current due to the rate of change in the charge I is equal to dQ by dt. On substituting the charge, we get the current I is equal to d phi E into epsilon naught by dt, which can be written as I is equal to epsilon naught into d phi E by dt. Let this be equation 7. This is the missing term in the Ampere's law, which is the current due to the changing electric field between the plates of the capacitor. This current is called displacement current, denoted as ID. Hence, Maxwell's generalization of the Ampere's law is that the sources of magnetic field are both the current in the conductor due to the flow of charges called conduction current denoted by IC, and the displacement current due to the changing electric field between the plates of the capacitor. Thus, the total current enclosed by the surface S2 is the sum of the condition current and displacement current, that is, I is equal to IC plus ID, which is equal to IC plus epsilon naught into d phi E by dt. Now, the Ampere's law can be written as integral over the closed loop B dot dl is equal to mu naught into IC plus ID, that is, integral over the closed loop B dot dl is equal to mu naught IC plus mu naught epsilon naught into d phi E by dt. This is known as the Ampere-Maxwell law. Let this be equation 8. In explicit terms, when the point P is considered outside the capacitor, the source of the magnetic field at that point is only the conducting current. Since outside the capacitor plates the displacement current ID is 0. Thus, integral over the closed loop B dot dl is equal to mu naught into IC. If we consider the point P inside the capacitor plates, the source of the magnetic field at that point is only the displacement current. Since the conduction current between the capacitor plates is 0. That is, integral over the closed loop B dot dl is equal to mu naught into ID. Even though there is no conduction current at the point P inside the capacitor, there is a magnetic field due to the displacement current, which is due to the time-dependent electric fields. Hence, the change in electric field with time can produce a magnetic field, and the change in magnetic field with time induces an electric field. This symmetry explains the existence of electromagnetic waves, which you will learn in another module. Now, let us have a look at the set of equations originated from different sources that helped the study of electromagnetic waves. These equations are popularly known as Maxwell's equations. They are integral over the closed surface E dot dA is equal to Q by epsilon naught. Integral over the closed surface B dot dA is equal to 0. Integral over the closed loop E dot dl is equal to minus d phi B by dt. And integral over the closed loop B dot dl is equal to mu naught IC plus mu naught epsilon naught into d phi E by dt.